kid.
You would have got
This watch would be Rolex, not Swiss Army. So have a nice pair of Yeezys or something.
But you know, once you get a job, I mean, it's any type of retirement funds, any type of contribution, then it goes into mutual funds of some sort, and then, you know, you can just set it. You know, if you're young, you can say, well, I think there's a 30, 40-year horizon. I'm telling you to cash these in, a retirement, so just let it go. Let the stock market do its thing, and don't pay attention to it.
Literally the only financial advice I ever got was a coworker told me once, like, you're young, you should have more stocks than bonds. And I'm like, all right, sounds good. And I was like, why is that? And they're like, oh, you're young, so if you lose a bunch of money, it's okay. And I was like, great.
Go aggressive, yeah. Try to get
Lose
that.
money if you don't make it in the first place.
Yeah. My childhood bedroom is looking real nice right now. Now we'll
Anyway.
start charging that at some point.
We're going to talk about five-area distributions. We're talking about more than one variable at a time, and then look at some of the mechanics of taking averages and what does that do to probability distributions, and so on. We do a bit of that, and then we state a few limit theorems, the limit theorem, law of large numbers, kind of some of the fundamental theorems of probability as they have implications for statistics. That's coming up down the road, and then do some applied calculations which result out of that. But to begin with, we set up information on joint distributions. So a joint distribution, right, is a distribution of two variables at once. Probability distribution. Joint distribution. This could also be called bivariate distribution. You could have a trivariate, so you could have three variables at once. Multivariate, essentially when we're taking n observations, you know, in different subjects and measuring the same thing on all of them. We have an n-dimensional one of these. The joint cumulative distribution function is going to be an f of xy. It's the probability that x is less than or equal to a value and y is less than or equal to the value of its variable. Right? Mostly, well, so that exists. So if you had x and y, what's the chance they're both less than some value? That there'd be a function that maybe would do that. Usually we're going to convert these into probabilities of specific events for discrete or density functions for continuous ones. So for discrete random variables, we're going to have the density of x and y, which is the probability density function. Not for discrete, sorry, I'm kind of writing the wrong thing. Right, a probability that of x and y. The probability that x equals a value and y equals its value simultaneously for continuous random variables. You differentiate this CDF with respect to x and with respect to y, so now it's two variables with partial derivatives of that. You get the probability density function, just in f of x, y. That expresses how kind of the relative accumulation of probability at a point or an area, and some function will describe that. If you have the joint distribution of these two things at once, let's look at one example. So on the page on the handout, so we have a copy of the handout. That's fine. So for a discrete one, you could have some variable like x, where people in the survey have been asked what's your attitude towards small cars, you know, are you favorable, neutral, unfavorable, kind of a marketing survey. And then y, something about personality type. Right? And maybe people would rate themselves, I'm a cautious person, I'm kind of a middle of the road person, or I'm more explorer, extreme. They might score themselves 1, 2, 3, but maybe there's a scale behind this. Like they asked about half dozen or a dozen questions. You know, would you prefer to go off-road with skiing or stay on the, you know, the trail? Would you explore, you know, would you like to go, you know, someplace and just go without a map and see what you find, or would you want your map, everything? And so, you know, a bunch of things, and then that gives a score, and then they classify people as one of these three types. Right? So each person gets they express their attitude, and they get a personality type, and they get these two things together. Right? In this case, there's 3 by 3 or 9 entries, and what's given there are these probabilities of the different things that are there. Right, so you could say, you know, 26.4%, the 0.264 of individuals are favorable and cautious. 19.4% are favorable and kind of a middle road personality type. Right? So you can read things off of that. And maybe that's based on a couple hundred people, 300 people, something like that, to get these proportions. I don't think it's necessarily a theoretical thing in any way, but probably more empirical. What we can do with either one of these things, once we have the joint, is if you average over one of the dimensions, you get the marginal distribution of the other one. So marginal distributions. For discrete random variables, the probability that x equals x, a probability function for x. You get it from the joint distribution of x and y by adding over the appropriate row of the probabilities that are there. And so this x is the same x, you know, all the way through here. So x is fixed. So whatever the joint probability is x with all the values of y that are possible, add up those probabilities and you get the margin. You can also get the marginal distribution of y. So in that, you take the joint densities, right, and add over the distribution of x. And so in this case, right, if you look at that, which of the categories about attitude towards small cars is the most common? Suppose I have this somewhere as a PDF. Yeah.
Favorable?
Yeah. So favorable, you add over the row, 0.264, 0.194, 0.164, and you get 0.622. Right? So by 62% of the people, at least in this study, right, are favorable towards small cars. Neutral is pretty rare, 9%, and then other people are unfavorable. Right? Or the marginal distribution of personality type. You know, you might suspect that because these things are roughly 1/3, you know, it's not exactly 1/3, but pretty close to 1/3, do people really divide up that way, or did they scale people and take 1/3 into each category to kind of break them up? But in any case, it's about 1/3 each for those, right? Those margins. Right? That's discrete, right? For continuous, so marginal distributions. For continuous, and we'll do some continuous examples in a bit. That the density for a random variable x, when you have the joint density of x and y, is an integral with respect to y of that density. So it integrates out that one dimension. The densities, right? The value x is the same value, fixed value of x that's in here, and you're just integrating out the y variable, so it's not there anymore. And that gives you a marginal distribution of y. You can do the same thing with the marginal distribution of y. You just simply integrate out x. In that function there. Now, with continuous or with discrete, you do have to pay attention to limits, right? Because sometimes x, y are related to one another. So if x is a minimum and y is a maximum, you can't have them be arbitrary values. You don't necessarily integrate over the whole space. So you kind of need to watch out for limits. In the sense that sometimes x and y are related, and really by that I mean that they restrict each other. Sometimes the sample space is a circle, right? So if you x plus y, x squared plus y squared has to be the radius squared, right? So if you have x, well, there's only a couple places that y can be, right? And so it restricts the range of what you're looking at there, right? So we did it for the discrete ones, right? Once you have the joint and the marginals, right, we can look at conditional distributions. So this follows usual rules for conditional probability. So for discrete cases, we can have the probability that x equals a value given that y equals one of its values. And conditional probability would be the probability that x equals one of these values and y equals its value over the probability that y equals its value. Or in terms of writing it in terms of this function, the joint density over the marginal density of y. Of course, you could look at it the other way. You could know something about x and then say what's the distributions of y. So it's y equals y, given that x equals x. It's again the density of both of them. It doesn't matter which one you view as first. Right there. But now the denominator is the chance of being at that level of x. So we could look at the examples again just to get conditional probabilities there. Right? So how does the distribution of x change depending on which level of y, what type of personality? Well, how does the opinion of attitudes towards cars change, right, as you have different personality types? There it is. So in fact, we could even make a table that's a little more extensive than what's there. We can look at the distribution of x given that y equals 1, the distribution of x given that y equals 2, the distribution of x given that y equals 3. So this one, the first person was this is the cautious type of personality based on the rating scale. And this one is the more explorer, more extreme, risk-taker personality. Right? And the values of x that we have are 1, 2, and 3. Right? And 1 was favorable, and this was neutral, right? And unfavorable. So we would look at the conditional probabilities. The chance of this one, of favorable, given the probability that x equals 1, given that y equals 1. From this table, what do you have to do to compute that? What's the numerator reading in the table?
0.264.
Yeah, 0.264, right? Both of them. And then we divide by the probability that y equals 1, right? Which is 0.30. So this one, 0.30, is about 80%. The second one, that x equals 2, given that y equals 1. Here. 2 and 1 is about 0.033. Again, the denominator is the same. It's still conditioning on y equals 1, so it's about 10%. This one also was 10%. So these conditional probabilities, adding over all levels of x with y fixed, have to add up to 1. At the other extreme of explorers, well, I'll give you the conditional probabilities. So there's 0.58 for this one, 0.08, and 0.34 here. Those add up to 1. And sometimes in tables, it won't add up to exactly 1, due to rounding. If all three numbers are rounded, it might end up being 1.01 or 0.99, and that's just the way it goes. So in a report, sometimes they actually want you to make a little note at the bottom of the table or something in the text that these things don't add to 1 because of rounding. And it's clear why that is. This one is 0.49, so the calculation of that last one. So x equals 1, y equals 3, 0.164. The chance that x equals 3, y equals 3 was the 0.335. So almost half of it is there. There's only 3% here, and this, oh, no, that says 9% as well. And 0.42. And those two should add up to 1. So if you had a bunch of characteristics of somebody and had some idea that they were more of this type versus this type, it looks like there's some difference in their opinions of these cars, right? So 80% versus 58 versus 49, it's decreasing there. The unfavorability, 0.1, 0.3, 0.42 was kind of increasing there. And so if you had to do marketing or you're talking to somebody, that's a little insight into slight differences, right, in their attitudes, right, what they might start out liking. You could display this conditional distribution in a graph, one way or another, right? One way to display this thing is called a segmented bar graph. So with y equals 1, y equals 2, y equals 3, we could put the conditional probabilities in this thing. So they add up to 1. So this all adds up to 1. In the first group, there's a little bit for both of these groups, but 10% for those, but 80% for the first group. So this is x equals 1, right? And up at the top is x equals 3, and the middle part is x equals 2. If you do comparable graphs for the other two, you can kind of visualize the difference in these conditional distributions. This is here, and this is here. This one is something like this, kind of a little spot in there. This one's a little bit lower, kind of a little spot. And this was in about, that's probably a little bit off of scale, 0.34, 0.42. And this top, oh, that's, sorry, I'm getting in the wrong direction. 0.58, 0.49 here, and then it was 0.34 and a little bit more here, 0.34, 0.42. So if it was actually drawn to scale, it might show a little bit bigger picture. Right? When you show that to somebody, what you're really communicating are the conditional probabilities. But any questions about? I don't think that's too terribly. It's difficult, but that's the essential idea of adding over one dimension or another dimension or finding a conditional. Right? So continuous ones, right, that there is this density as a continuous example, and so we could have a conditional density that is something like this. Right? There's some constant C, and x and y are in some interval, right, as the probability density function. And if f is x kind of y is a probability density function, right, then the integral over the density of dx dy has to be 1. The integral of the density over the entire space in which it's defined is 1. Right? So we can use that to find C. Right? So if we take this density, I'll pull the C out. In this case, it doesn't matter whether you do dx dy or dy dx, which order you do it, it's going to be the same thing. X and y in terms of their space don't interact with one another, so both of them go from 0 to 2 or 0 to 2, the letter y. Right? So after calculus 1, you might not have seen bivariate integrals, but most of these examples won't be terribly different than single variable calculus ones. It's just we do one at a time. And so with respect to x inside of there, it's an x squared over 2. And with respect to x, y is just a constant. Y is just another number, not a function of x. So the integral is just y times x. We evaluate that at 0 and 2 inside of there. Right. So there's a c, and then an integral from 0 to 2 of 2 plus 2 times y. And when x is 0, both of those go away. Right, so now we have to integrate that part. Right. And so it's a c times 2 times y plus y squared, and y going from 0 to 2. So we get c times 4 plus 4 minus 0, or c times 8. That's supposed to equal 1. So that constant in probability, these things are called like a normalization constant, so it normalizes everything to be integrated to 1. So our value of c is x is 1/8. Right? So our density f of x, y, defined on that square, 0 to 2 square, is 1/8 x plus y. And that's just the probability density. So as x gets bigger, or y gets bigger, or they both get bigger, right, the density is increasing. Right? There's more chance of bigger observations. Right? So it's not flat. It's not like a uniform flat over that 0 to 2 square. It's increasing as x and y get bigger, values are more likely. So that's the density. What's the marginal density of x? S of x is going to be integral of the density over y. And again, y isn't restricted by x in any way. So it's just that integral. So there's 1/8 x y plus y squared over 2. And then y is evaluated those couple of places. So it's 1/8 and then 2y plus 2x. Sorry, y is getting filled in. 2x plus 2. So it's 1/4, x plus 1. And x goes between 0 and 2. So that's the marginal distribution of x. what do you think the marginal distribution of y is? This one's completely symmetric, right? So what are you going to say?
The integral from 0 to 2, 1/8 x plus y dx,
Yep. 1/8 x plus y dx.
which likely evaluates to 1/4 y plus 1.
Yeah. Yep. Because the density, the marginal density is exactly symmetric, I mean, the ranges are the same, the integral works the same. Okay. What's the conditional distribution? Given that you have a value of x, what's the density of y? So let's do f of, say, x given y first. If I needed to make another subscript on that to kind of indicate which variable I'm talking about, so if I wanted to do the conditional density, I like to put subscripts on there to keep track of things. It's a little, maybe you can kind of figure out what you're talking about, x given y, from just that, but that makes it a little more explicit. I usually write capital letters for random variables, and then the lowercase letters for the values, just to keep track of everything. If you go on to a graduate program, it's mathematics, if you do probability, or measure theory, or statistics, you have to take more courses in this. It gets a little more involved, but it's useful to keep track of things. So anyway, that's a system I use. So how would we do this one? Well, it's just a ratio. So it's the conditional distribution. So this one is given y. Right, what is the PDF of x? What's the probability density function for x, given that you have a certain value of y? So f of x, comma y. And then we have the marginal distribution of y in the bottom. So it's just a ratio of those two functions with a statement about the range of x where this is permissible. So 1/8 x plus y over 1/4 y plus 1. So that's like 2 times x plus y over y plus 1. And x can go over all of its 0 to 2 range. So given y, the distribution of x still has that value in there, whatever y happened to be. So if you had a specific value of y in mind, you could make this more specific. Right? So if y is 1, say, right, then the density of x, given that y is 1, is 2 times x plus 1 over 2. Right? Plugging y into that. And so it's x plus 1 on that range. Does that really work? Have I done anything right?
Why is there a 2 in the numerator?
Why is there 2 in the numerator? Should there be should be a 2 in the denominator? Is that right? 1/8 over 1/4, so there should be a 2 in the, I kind of did those, I reversed that, sorry. So that fixes things up, right? So there shouldn't be a half up here. There should be a 2 times, right, 1 plus 1. So it should be x plus 1 over 4. That looks it better. I think that's actually going to get to 1. That should be the difference. I did the 1/8 over 1/4 wrong.
Do we need a range for x and y?
This one, so yeah, so this is, whatever y is, right? We can choose any value of y in this. But once you choose a specific value of y, then there's only one value of y that's in there. Right? It's given a specific value of y. Like given that y equals 1, then it becomes this function. If y is different, then x conditional on that has a different density, it changes. Right, so for instance, if y equals 3/2, then the density of x given y equals 1 is x plus 3/2 over 2 times 3/2 plus 1. Which simplifies to 3 is there's a 5 here. And then the x plus 3/2, maybe I'll multiply by 2 on both of these, 2x plus 3, and multiply by 2 again on the bottom, you get a 10. So that's 2.5, 5, multiply by 2 again, you get 10, multiply by 2 up here, and just for making it look nice, it's not a fractions over fraction. So those two things, are two different functions, right? And so they are different densities. And so if you plot them, right, so x goes between 0 and 2. One has the top one has an intersection of 1/4. 3/10 is, well, that's 0.25. This one has an intercept of 3/10, so that's 0.3, so it's a little bit bigger than that. And this one has a slope of 1/4, whereas this has a slope of 1/5. So this one is going up a little bit higher, and this one's going a little bit, lower, right, with this. So this is the 1/4 one. So this is when y equals 1 is the density for x. This is the f of x given y. Right? And the dotted one is more when y equals 3/2. So when y is 1, x is more tilted toward the big values. Right? But when y is 3/2, x is not quite as tilted toward the big values. It's still tilted up a little bit. I haven't drawn it very convincingly, but it's still tilted up a little bit. So between these two cases, it affects, the value of y affects the value, likely values of x. Right? We're going to do expectations, so we can let's look at this one, right? There's something called conditional expectation. We will return to this in a bit, and spend a little more time on this idea of conditional expectation, conditional variance, things like that. There's a neat decomposition that's kind of critical to thinking about hierarchical models and more complex structures, right? But it just simply means take the expectation of x, given that y is a certain value. That is, in the continuous take the derivative, the integral of x, expectation of x, we always take expectation of x. The conditioning part means we don't use the density of x, we use the conditional density. We use an example of x given y. Conditional. We'll talk about this more, but in this case, it kind of is useful to illustrate how the changing conditional density impacts kind of the average value of x, right? So in the first case, when y equals 1, the conditional density when y equals 1 was x plus 1 over 4, right? The f of x given y. So it was x plus 1 over 4. So in this case, the conditional average of x, given that y equals 1, is this integral over the values of x times conditional density, x plus 1 over 4 dx. And so there's a 1/4. Pull that out. Integrating the top is an x squared, so it's an x cubed over 3 times x, so it's an x squared over 2, and then x goes from 0 to 2 for this one. So given that y equals 1, we expect on average x to be right, as an average. It's a little bit bigger than 1 on average. What happens to that average, though, if we know that y equals 3/2? Then the conditional density was that other density. And with 3/2, the 3/2 picture's a little flatter. What's going to happen to the average of x if the density is a little flatter? It's going to be a little bit less, right? Pull it back. So if the density is not quite as favoring the high values of x, but more even, right? So this one, 2x plus 3 over 10. This 2x plus 3 equals 10. And then the expectation of x, given that y equals 3/2, is an integral. Expectation of x is an integral of x times some density, because it's a conditional density that we're working with. Right? We use that one. Put in 2x plus 3 over 10 dx. I'll pull the 1/10 out. So 2x squared becomes 2x cubed over 3. And then 3x, the integral becomes 3x squared over 2. X still has the range of 0 to 2. So 1/10, 2, 4, 8, 16 thirds plus 2, well the 2, we cancel that, that's nice. So there's a 2, so there's a 6. What is this thing? So 6 is 18 thirds, so this is like 34 over 30. And right, so if you put everything over 360 to make it maybe that's not the greatest. 60 is a better least common multiple. Will work. You don't have to go all the way to 360, right? 60. So that's 68 there. Multiply by 5. That's 50. That's 70. So this average is a little bit bigger, right? Because the conditional density of x is a little more tilted up toward the positive values, more density on those when y was 1. Right, so they affect each other. And if we have these functions, we can see how they go. But any questions on this?
Did you scroll up just a little bit?
Yeah. So we often ask a question for random variables. Are they independent of one another? In this case, do x and y seem independent of one another? Probability of one affect the other one.
Don't seem independent.
As y changes, the density of x changes, right? So that's the dependence that we're talking about. If you know something about x, you change your opinion about y. Right? The conditional probabilities, conditional densities change, then no, they're not independent. Right? So independence also gets presented. We can start with the definition of independent random variables. Right? X and y are independent. Random variables give the joint density, joint cumulative density of x and y is the product of the two. Right? Now the probability that x is less than or equal to x and simultaneously y is less than or equal to y, which is that tau capital F X Y is the product that X is less than or equal to its value times the probability that Y is less than or equal to that. So when we did elementary probability, we said two things are independent of one another. We said the probability that both things happen is just multiplying the two probabilities together. And it translates over into random variables in terms of these cumulatives. All right? So for discrete random variables, this is equivalent to saying that X and Y are independent if, I guess I should say all pairs of X and Y, right? So it has to be hold true no matter what X and Y are. It can't only be for a few specific examples. It has to be true over the whole space. When they're discrete, this cumulative things translate into, if it holds for that, it has to hold for all pairs of X and Y, because you can, augment, change X by 1 or Y by 1. So it means that the probability that X equals X and Y equals Y is the probability that X equals its value times the probability that Y equals its value of all X and Y. So if you figure out the marginal distribution of X and the marginal distribution of Y, and multiply two probabilities together, if it doesn't equal the X and Y joint probability in there, it's just not independent. It has to work for all of them, yeah.
Why for continuous random variables do we use the CDF as opposed to the PDF to test their?
So, for this works for all random variables, whether it's continuous or discrete. That's the kind of general case. And discrete, we kind of usually implement it by looking at just the probabilities at points. But for continuous ones, we will. For continuous ones, the counterpart to that is that the joint density factors into f of X times f of Y. If that's the case, then they're independent. Right? One implication of this is what's the joint density? What's the conditional distribution of X given Y? What's the conditional distribution of X given Y? How does it simplify if they're independent? Going back to the definition, right, of conditional, you get the joint density of both over the one you're conditioning on
Equals f of x of x.
Yep. Yeah. So if they're independent, or Fy, it's just the density of X. Y is gone from the formula. It didn't have any impact on it, the marginal density of X. Didn't exchange information about it in one way or other. So they're independent. So if this holds for all values of X and Y, then they're going to be independent as well. Right? Because you could, the joint density is this one times that always. But if this one always simplifies to f of X, then you get it like that. Right? Similarly, then the conditional distribution of Y given X is just Y. It doesn't depend on X at all, right? And so we use, if there's random sampling and each person gives an answer, maybe each person's answer comes from some normal distribution, and they're independent of one another, then the probability of two things gets multiplied. We used it with the case of two random dice in a discrete case, so if you had the numbers 1, 5, and 6, you go 1, 2, 3, 4, 5, and 6, and we said that each die is fair. Right? This fairness, right, translates into the, so this is die 1, and this is die 2. That fairness turns into 1/6 chance for each of those outcomes, right? Equally likely outcomes. Each. But the independence means that if we have two different values, probability that the first one and the second one is some two particular values, A and B. Right? Because of independence, it implies that you can just multiply those two together. This is because of independence. You could have independence even if both dies favored the number 6, right? If they were slightly weighted differently, and 6 tended to come up a little bit more, maybe 6 and 1 tend to come up, and I don't know if it's weighted that way physically, but if you could, the probabilities don't have to be equal. You could still have them independent, where you just multiply the probabilities together, right? So if it's 1/6 for each of these, right, it's 1/36 overall, and so of these 36 possible outcomes each year, they all had the same probabilities of occurring. And we looked at things, there's a lot of different ways of taking two die that you roll and turning it into different variables, right? So these two variables, the values on the, we could define new variables. We could say what's the maximum value and what's the minimum value that we have on the two dies. And have certain probabilities on these different variables simultaneously together, and a key step in computing the probabilities of different outcomes. Like, what's the probability? We'll just do one of these. The maximum, say, is 4, and say that the minimum is 2 on this. Well, where does the maximum? Well, that's a little bit too. That's very specific, right? Well, we can do something. We don't have to do it backwards, right? So the maximum, right, on these dice, the maximum could be 6, right? We get 6 on 1, we get 6, right? But it could be 5 or 4. The maximum could actually be 1. On these things. What's the probability that the maximum is just 1? There's only one way that can happen, right? You get 1 on both of them. How many ways can we get the maximum being 2? Here's the maximum, 1, 4. So, first one could be 2, or the second one could be 2, right? Or they could both be 2.
Or they could both go.
Or you can have a 2 and 1, 2 and 1. Right? You can have this gives a maximum of 2, this gives a maximum of 2, and this gives a maximum of 2. So there's actually those 3 possibilities there. Right? The probability each of one of these by independence is 1 out of 36. So there's 3 out of 36 for this. Going to 5, there's 5 out of 36. 5 out of 36. Then 7 out of 36. 9 out of 36. There's actually 11 ways that you can get 6 as the maximum. Any of the numbers, right, in this row, if 6 occurs on the first one, or 6 occurs on this one. There's not 12 because there's the duplicate in here where they're both 6. But anyway, those are the probabilities, right, of the maximum. What values of the minimum are possible? Can we always go 1, 2, 3, 4, 5, 6? Well, marginally, the minimum happens, the probabilities are reversed. It's 1136, 936, 736, etc. The chance the minimum is, I'll erase this word here, the minimums is 1 out of 36, and 3 out of 36, and 5 out of 36. Are the probabilities of these as minimums, right? The minimums occur, right, that the minimum being 6 only happens in one place, right? If the red numbers here are the minimums. If they're both 6, the minimum is 6. But if you get a 5 and a 6, right, the minimums are 5, and then 4. And so it counts kind of the distributions of X. Minimum and maximum are kind of mirrors of each other. But when you have the joint distribution, are all 36 possibilities still possible if you're looking at the minimum and maximum as two things simultaneously? If the maximum is 1, and you have a minimum of 2, you're stuck, right? If the minimum is 1, right? If the maximum is 1, you only can have a minimum of 1. You can't go above that, right? If the maximum is 2, well, you can have a minimum, right, of either 2 or 1. And so it's restricted. So these are possible at 3. When the maximum is 4, the minimum could either be 0, 1, 2, 3, or 4. And this, right? And this one is all 6 values here. And that's possible. If the maximum is 6, the minimum could have been anything. You just a 6 on one of the die, and you could have the other one be anything, and that defines the minimum. Right? And so what are these joint probabilities? What's the probability, say, that you get? Okay, let's take that one. What does that one correspond to? The maximum is 5, and it says the minimum on this row, right, is 3. What's the probability you would get a 5 and a 3? How many ways can this occur out of all 36 possibilities? Let's go back. So where does that special case come from? So die 1, you can have a 3 on this one, and then you have to have a 5 on this one, right? 3 and 5, minimum 3, maximum 5. Right? What's the other way it can happen? 5 on this first one, right? And then a 3 on this one. So there's a couple possibilities that give you a certain maximum minimum combination. So the probability of all of those dots is 2 out of 36, or 1 out of 18. What about on the diagonal here?
There's only one possibility of each.
Yeah. If the minimum and maximum are the same, those two values have to be the same, and there's only one way that can happen. Right? So would be 5 and 5, the maximum equals 5, minimum equals 5, and so the probability is just 1 out of 36 for those. These are on diagonal ones. Diagonal. And then it's going to be 2 out of 36 for the ones that are off the diagonal. So that, it's kind of like that table of 36 that's been kind of folded in half and added up the probability. And those are the minimum and maximum independent of one another. What would common sense say are the minimum and maximum independent of one another? If I tell you the smallest, if I tell you the minimum is 3, does that affect what you think the maximum is? It has to be three or more, right? It can't be less, right? So these things are affecting each other. You tell me one thing, one of these two, I have a little bit of information about what the other one is. Maybe I have a lot, right? So if the maximum is 1, I know what the minimum is, right? It's determinate. But if you tell me the maximum is 6, I don't know all that much about those other ones. Right? But the probabilities are changing, right? So in this case, I'll put it on here, right? So maximum, and minimum are not independent. If you take any two numbers, right, say the minimum of 3, and the maximum is 5, well, the joint probability is 2 out of 36. Using our definition of independence, we multiply the marginal probabilities. What's the probability that the minimum was 3? Minimum of 3 was 7 out of 36. 7 out of 36. What's the probability that the maximum is 5? 9 out of 36. Kind of marginally, it was 9 out of 36. You multiply those two together, right? It's 63 out of 36 squared. If you put this under 36 squared, it's 72. And those things are not equal. You can't multiply two marginal probabilities to get the joint, so they're not independent. We also just know logically that they restrict each other in their space. If you know that the maximum is 3, there's only 3 possibilities. There's not all 6. So some of these are probabilities up here are all 0 actually, right? Because the minimum is never bigger than the maximum. Right? And if you multiply two non-negative numbers together, you never get a 0. So they're just not independent, no matter how you look at it. But anyway, any questions about this kind of? For continuous random variables, there's an easy way to see if things are independent of the density. X and Y are independent if and only if the joint density of X and Y can be factored into one part involving X and one part involving Y, with the constant number multipliers put into one side or the other. So all the X part is on one part and all the Y parts on the other. You multiply and you get the density back. Why does this work out? Well, it's, if you have to prove this, right, you would want to prove it one way and then the other way, right? So going this way, right, and you assume X and Y are independent. That means, based on how we've defined things, that f of X of y, f of x, times f of y. So it's obvious that you can write the density like that into an x piece times a y piece. That's exactly what's happening here. Going the other way is the case that's more interesting. So assume f of x can be written as a function that involves x's. Can we then convert that to a can we convert this to f of x, where it's actually a probability density function, not just any old function, but a probability density function. Right? When you actually find those two things such that the density is a multiplier, you have two densities times each other, not just arbitrary functions, but it actually works out there. And it turns out that you do, right? You can do that. Just integrate out y from that, you get, which is g of x over a constant. Or if you integrate out x, you get h of y over a constant. And you take h over y over one of those constants and g of y over one of the other constants. Those are both probability densities, and so they multiply. Right? So yes, it works out. If you can factor it, you can find the densities that they actually are, and it works out. So if you integrate f of x, y, say, with respect to y, under that assumption that it can be written as g of x, h of y, dy, well, x is not involved in dy. Right? dy is how y is changing. There's no y in that, so it's a constant. So g of x comes out, and it's h of y, dy, whatever that is. This is how we found the density of x. Density of x is this, and we can integrate that, and it ends up being that's the marginal of y under this assumption, right? We integrate f of x and y dx. So we would integrate, by our assumption here, is this factors. With respect to x, the y doesn't have any role, it's not changing. So h of y gets out of here, and it's this thing g of x. Dx is left over. So these two things really are, they're integrals. Once you integrate out the thing over its range, it's a constant, right? It's like integrating something over, a definite integral and putting in values, right? The result is a constant. It no longer involves y. If you integrate out y, it's gone, right? So this is just g of x times a constant. So this is like g of x times a constant, specific to x. And this is h of y times a constant, specific to y. Right? Right, so does f of x, y equal f of x times our f of y? Does it equal that? Well, we've said that this thing is our g of x times a constant. How does this work out? Times constant of y. It's g of x. Right, want to say that this thing integrates to each of these things integrate to 1. So it's like almost just kind of like just goes through. Yes. What?
So like in the instance where we're being asked a question like, are these two independent?
Yeah.
Would we be given f of x, y, g of x, and h of y?
So the kind of question, so let's say f of y equals some constant, I don't know what it is yet, times negative x plus 2y. And 0 is less than x is less than 20, and 0 is less than y is less than 20. With an appropriate choice of the constant, that thing's going to integrate to 1.
Mm-hmm.
Are the random variables x and y here independent of one another?
So I break that up into two functions, e to the negative x times e to the 2y.
So you could call this part g of x. You could call this part h of y.
Okay.
And so yes, you will be able to integrate out x and you'll be left with y. It won't involve x in any way. And so, so yes, the x and y here would be independent because of that factorization. The other case that we had earlier today was there's 1/8 x plus y with 0 less than x less than 2 and 0 less than x, y less than 2. Are x and y independent? You can't split that in time x times y in any way. This cannot be written in as a g of x times of h of y. So, not independent. You could go about the process of finding f of x and f of y, right? And if you did that, they would not equal the product. One was, you know, like it was like 1/4 x plus 1. It was something like 1/4 x plus 1, right? And this one was 1/4 y plus 1. You multiply those two together and it's not this, and it's not equal. So it's not independent. The conditional densities were changing as like, you know, different value of y, you get a different distribution of x, they affect each other. They change their probabilities and they're not independent. But this, just using that factorization is a quick way to check. And it works. One complication with this, sometimes we go tricky. So y equals some constant times e to the negative x plus 2y. Let's say the range is 0 is less than x, is less than y, is less than 15. Now this constant c is some number such that the integral over both x and y over the appropriate space does integrate to 1. So it's a probability density. It works fine for that. But are x and y independent of one another? Well, it would look like we can factor this thing, right? But I guess I should say this thing is 0 otherwise. But where the little wrinkle on this comes down is we've put some of the information right into here. Right, we put a bound in there. So just right away, we know that whatever x is, y is going to change, right? Y can't be less than x. So the probabilities have to be changing because of that, right? So if there's a restriction in the range of the, like there was for minimum and maximum, They just can't be independent, because one prevents the other one from having probability at a certain space. How do you get that with the factorization? Well, if you write this thing, another way to write this function here, this density, you can have x less than 15 and y less than 15 and still be equivalent to this. And sometimes people you could put something called an indicator function, right? A 0, 1 function. Maybe you call it the delta function or a Dirac delta type function. I call it an indicator, which is true if x is less than y. Right? So this thing is going to be a value of 1, right, if x is less than y, and 0 otherwise. And the density is 0 otherwise as well. Or elsewhere in the space. Right? So, x could go from 0 to 15, y could go from 0 to 15. This incorporates that restriction into there, and there's no way you can break apart x and y in that restriction. Right? So factorization, if you take logical things like this out of the range, right, and put it into the density function itself and encode it there, that can't split. So this thing cannot be written as a g of x times h of y, right? So not independent. So that's kind of a technical way to use that factorization theorem in this case, right? But just from logic that x and y restrict each other, so it's just not going to be independent. But any questions about things related that we've done so far? So the last thing we're going to do today is expectation. We've done some conditional expectation as just as an example, but in general, when we have two variables, x and y, we can be interested in anything related to the values of x and y. We can do any type of function of them. We can take the difference, we can take their sum, we can take the maximum, minimum, we can take any of those functions that we might be interested in. A function is usually written as g of x, y. This doesn't have anything to do with the other g of x function here. This is just a new function. And we can take the expectation of that function over the joint density of x and y. The expectation. Maybe you could call it a new variable, maybe capital G. Over or with respect to the joint density, joint probability density. Of x and y. In the discrete case, we take all possible combinations of x and y and the g values, and then take all the different possibilities times the probabilities. So in the discrete case, is what we're probably going to do primarily today. The expectation of g of x, y. The sum over all values of x, sum over all values of y, of the function. So the g of x, y is the sum of the two, or the difference of the two, or whatever you want to take. X times y times the probability that x equals x and y equals y. So this would hold true if g of xy is simply x. If you only want the expected value of x, you don't necessarily have to find the marginal distribution of x and then take its expectation. You can go straight from the joint. But it's more interesting if it involves both x and y. For the continuous one, it's the same version of that. The expectation of, call that the g up there, so I'll write it like that. The integral, double integral of gxy times not the probability, but we use this f symbol for probability density function, and then dx. Or you could reverse dy dx, and sometimes it doesn't matter. Sometimes if there's restriction on the space, like one's less than the other one, then it's easier to do one or the other. But right, that interval. So let's look at that at another example. So the page 2 of the handout is called example 1. Sometime in the past I made up this handout and I can't find the original document, so I'm stuck with examples always being given these numbers. Right? So imagine you're asking people about insurance. You have car insurance and they have collision insurance, right, which they pay if somebody hits them, right? And then liability insurance, that if they hit somebody else, they have to pay for that. So 2 different types of insurance. You can set them at different levels. And imagine that they have $20,000, $40,000, or $100,000 insurance of each type. And they can pair the $20,000 collision with $100,000 liability or any other combination. And so then there's the 9 joint probabilities that are listed there. We could do some of the things that we did before. You can find the marginal probabilities. What % of people have 20,000 liability? So if you add down the column, right, you get the 45% have that. Maybe let me see if I get this conveniently so you can see where I'm looking at. There it is. Okay. Right. That's the car one. We're looking at this one. So we can find the margins if we wanted to. 45% have 20%, 20,000 liability, 35% have 40, and 20% have 100. And it looks like it's the same probabilities going that way. What's the chance you have 20, 40, or 100 collision insurance, given that you only have 20% liability? So 30% out of the 45 is 67%, 10% out of 45 is 22, 5% out of 49 is 1 out of 9, so it's 11. On the other hand, if you're in the final column and you have 100,000 liability, what are the rates of having the different collisions? 5 out of 20 is a quarter, 10 out of 20 is 50, 5 out of 20 is 25. Are these 2 variables independent of one another? Generally, there's more probability. Well, there's 50% on here. There's not too much on the other. So it's kind of, they're both kind of increasing together. It's kind of a positive association. But we can do various expectations, right? What's the average collision? What's the average liability? If we have the margins, it's convenient just to do that. Right, 20 times 0.445, 40 times 0.3, 100 times that. So on average, people have 43 or 43,000 in liability. It's symmetric on the 2 things. It's also 43,000 there. But instead of finding that, that way, what the formula for the joint says is we could take, if we're only interested in x, our function g of x is x, right? G of xy is x. So if our g of xy is simply x, only x. What this thing says is, the expectation of x, or g of y, is a sum over all the x's, a sum over all the y's of just x, because we're only interested in x, times the joint densities. I'm going to reverse these for this case. Just because no, I'm not. I liked it. That was good. Like it like that. All right. So it says you can go take the value of x times all of those individual probabilities for it. Right? So we could go to this thing. We could take 20 times 0.3 plus 20 times 0.1 plus 20 times 0.05, and so on. 40 times those three, 100 times those three, and add them all up, and that's the expectation. It's equivalent in this case. Now, x doesn't depend on y, so you can pull x outside of y summation on p of x, y here. And so if it's only x, this thing, if you add over all the y's, is a probability of x. And that's how we just had one distribution, one variable, is how we would think about doing that. But this joint probability says we can take the value of x times all the individual probabilities and add them up. Similar type of thing for y. X squared, we can take expectations of those. So we might compute the variance of x and y as 891, standard deviation of those two things, about 29.85. It's about $29,850 standard deviation. Right? Conditional densities. We will do a little bit more of this transformation here. Well, so what's the expectation of x plus y over 2? Right now, our g of x, y. What's the average dollar value? So now our g of x, y is the average. We have a couple of ways to go. We could try to figure out the distribution of x plus y over 2. Right? All the values you can take on, all the probabilities, and take the expected value of that new thing. But we don't necessarily have to do that. We don't have to figure out what is the probability density of this thing. Right? List all the x plus y possibilities. I don't know if there's exactly 9 of them, but there would be 9 of them, right? Because some are symmetric in this case, so there's probably 3, 4, 5, maybe 6 different unique values. And then 6 probabilities for that by adding up the right thing. Kind of like we did with that die example, 6 by 6. When we did maximum, minimum, there ended up being a few different possibilities. Well, we got the maximum, right? Then we had a probability for that. We could do that for this average, but we don't necessarily have to. Right? We can, the expectation of this average, right? Sum over the x's, sum over the y's, x plus y over 2 values times the probabilities, and we get an expected value. This is how we did it here. Right. So if you have all the x, y combos, here's the average, here's the total, here's the absolute difference. These are the probabilities for 20, 20, 40. Here's the probabilities for each of these pairs. So to take the expected value, you can take 20 times that, 10 times that, 30 times that, and so on, and get the expected value of the average, or the expected value of the total, or the expected value of that difference. Or if you wanted to, you can see that in x plus y, 60 gets repeated, 120 gets repeated, 140 gets repeated. So there's some repetition there. You could collapse it into the unique values and the unique probabilities and take expectation this way, right? These unique values times these probabilities added up would give that expectation. So it turns out the average is 43,000. We follow through with the variance and standard deviation of this average. The standard deviation is about 23,000 on the averages. It's the average of 2 things, so it's a little bit less variable than either one individually. Right. Or you do it with the totals, or here's the thing with the difference. Right? The difference comes down to those are the possible differences in their probabilities, and you could find the value just like you would for one variable. Right? So that's the general scheme. We can take expected value of different things we're interested in, either by finding the marginal probability of the specific function we're interested in, or just adding over all possibilities of x and y, right? Where our function is the value we're interested in, and we use all 9 probabilities in this case, add it up. It works to give you the same answer. We're probably going to come back to something like this last one, and do a little bit more with a specific special function. There's a special function called covariance, and then something related to that called correlation. So for numerical variables, we can measure association. Do they tend to increase together or decrease together? And what we'll come back with covariance. We will investigate this expectation. The covariance of x and y is the expectation of x minus its mean times y minus its mean. And if x and y tend to be big together and small together, and positively associated, this thing's greater than 0. But if it's just random, if there's no association, it's 0. If x and y trade off, like if people are budgeting and they're only going to pay for so much insurance. So if they pay for 100,000 liability, they're going to tend to pay less, 40 or 20 for collision. If they have a budget and they tend to trade off, one goes up, the other one tends to go down, then covariance will be less. This thing simplifies. If you multiply all this out, x times y, use of x times y, x times y, and then use of x, use of y, as you multiply that out there. The expectation of y is the use of y, the expectation of x is the use of x, and so we end up with an expectation of x times y, right? This is one of these functions of x and y, right? The product of the two. It'll be like one of those g of x, y functions minus the product of the two means. And that's our covariance. We'll illustrate that with some more numerical data. So that's a big introduction to joint distribution, finding margins, finding things, determining if something's independent of one another, and we'll do more fun stuff.
Oh, you get your crypto back. Sorry. Thank you. Have a good one. Bye.
Yeah, you want to add it? Yeah. You going right now?
I think we're about to really go
Wait, is that really good?
Yeah.
That's good. Thank you.
Good one, Jim.
Realized that I was on the iTunes account, so I liked it. But whatever.